Hello everyone, my name is Brian and this presentation is a lecture on the core ideas of the Fast Fourier Transform algorithm. My goal is to present to you the intuition behind the algorithm from the high-level setup to the ideas and to the pseudocode. What is a Fast Fourier Transform, or FFT? FFT is a fast algorithm for multiplying polynomials. I choose to introduce FFT to the utility of polynomial multiplication because this is how our CLRS book does it. And also I think it's appropriate because it's something general and we've gone through this before in high school mathematics. Uh, it's an algorithm that combines ideas from computer science in the form of divide and conquer strategy and from general mathematics in the form of complex numbers. Let's take one slide to mention some applications of polynomial multiplication. Primarily, it applies to an operation called convolutions, which itself applies to many other areas listed here. There's machine learning, as mentioned in previous presentations. We also notice there's Fourier transform in signal processing. Difference is that Fourier transform is a general concept in signal processing for transforming signals from their time domain to their frequency domain. Meanwhile, FFT is the procedure itself, or the algorithm. So let's review the concept of polynomials. So it's a function on only one variable, usually indicated with x. It has terms, which are the individual members of the polynomial, including the sign, the degree, the highest power among the terms, and the coefficients, the values here, a0, a1, a2, and so on. So for example, polynomial px equals 8 plus 2x minus 9x cubed is a polynomial with degree 3 and 3 terms. So the naive way to multiply polynomials, I think you can already imagine how to do it. So multiply each term from one polynomial with all the terms of the other, add up results of every product, and then finally add up results for all the rows of the sums of products, correctly adding up terms of the same power. So it's like multiplying two integers the way you would do it manually. So the problem here is that this is too slow. It takes a quadratic time complexity because of this sort of loop in a loop part of this direct algorithm. Before we can do polynomial multiplication, we need to represent polynomials computationally. So there's two major ways to do it: coefficient vector and point value pairs. So in coefficient vector representation, we extract all the coefficients and put them on inside a vector. So for example, p equals 8 plus 2x minus 9x cubed has the following coefficient representation. So it would be 8, 2, 0, negative 9. So notice that this polynomial doesn't have an x squared term, but in its representation, we need to fill that up with a 0. On the other hand, we have point value pairs. So it is any set of point value pairs of size degree plus 1 or more. And we will see why we're adding plus 1 or more here. The points must be distinct, and the values are simply the evaluations of the polynomial at those points. For example, p equals x squared plus x plus 1 can be represented by at least degree 2 plus 1 equals 3 points, because you need at least 3 points to represent a parabola. In this case, the points 0, 1, and 2, and then evaluated at 1, 3, 7 respectively. Of course, you can choose any set of points to represent a polynomial. The key idea here is represented in bold in that the elegance of the fast Fourier transform has something to do with the clever choice of point value pairs, as we will see later. So comparing the representations. So for the coefficient representation, it can intuitively represent the polynomial, as you can imagine. Just extract the coefficients, put them in a vector. If you want to write them back again, just append uh, the x powers. However, multiplication takes quadratic time. That's what we're trying to solve here. But evaluation at a certain point simply takes linear time. You just have to plug in the point and solve. And this is dominated by the number of the terms in the polynomial. So it's straightforward. Meanwhile, for point value representation, it's not intuitive for representing polynomials. Because you can imagine it's just a set of point value pairs. Multiplication takes linear time. So this is the good thing. Multiplication is pointwise, meaning you simply evaluate the points at polynomials ax and bx, for example, and then multiply them pairwise, and that's how you get mx. So this means that while point value multiplication is faster than coefficient multiplication, we need to sample more points for each polynomial. We will see this later. We will come back to this, but uh, it's still better than quadratic time. As for evaluation, given a set of points, solving a point not in the original set of the point value pairs requires interpolation, and this takes quadratic time using Lagrange's formula. So the high-level view of the problem is this. We start with the coefficient representations of the input. We also want the coefficient representations of the output. But if we take this straightforward path, we're going to take um, we're going to take big theta n squared. So the idea is, given that naive multiplication takes quadratic time, what if we convert to point value form, do the faster pointwise multiplication, and then convert back to coefficient representation? But for the moment, uh, the naive computation for evaluation takes n squared, and interpolation via Lagrange's formula still takes n squared. So how does FFT speed up the multiplication? So FFT helps in both evaluation and interpolation. So evaluation will be done using FFT. Interpolation will be done using inverse FFT. So as you can see, the overall time complexity would be n log n plus linear plus n log n. So in total, n log n. The elegance of FFT starts from here. So the slides prior to this, that was just a setup for in how to compute polynomial multiplication computationally. So this is the start of the actual FFT. So the first core idea is to reduce redundancies in evaluation. So consider A with coefficients a0, a1x plus a2x squared, a3x cubed. What if we choose one negative 1 as inputs? Remember, in point value representation, we can choose any point. So there's freedom here. If we plug in 1, we get a0 plus a1 plus a2 plus a3. But if we plug in negative 1, we get a0 minus a1 plus a2 minus a3. So you notice that to evaluate ax at 1 and negative 1, we require 1, 2, 3, 4, 5, 6, 6 additions. So the idea is it is split A into 2. So that would be A even and A odd. For A even, we only take the evaluations at the even index coefficients. So that would be A0, A2. For A odd, that would be A1 and A3. So what happens if we use 1 and negative 1 here? Notice that the evaluations at 1 and negative 1 become A1 equals A even plus A odd, and A negative 1 equals A even minus A odd. So the point is, we compute A even once and we compute A odd once, and then reuse the computation. So now it only requires 4 additions. So 1, 2, 3, and 4. So can we generalize this? So the second core idea is try to make the redundancy reduction recursive. So for our divide step, at every level of recursion, we split the polynomial into two polynomials, one with even index coefficients and the other with odd index coefficients, as follows in general. So we define a even x equals a naught, a2x, a4x squared, a6x cubed, and so on. Same goes for a odd, except we take the odd index coefficients from the original bigger polynomial and give them new powers of x. And then eventually we will evaluate these two functions at positive negative pairs of numbers. For the combined step, when splitting the polynomial in two, the powers are half, if you notice. So to recover the bigger polynomial, we square our inputs. The terms with odd powers need to be recovered as well, so the odd function needs to be multiplied by the variable x. So to get back the original, at every combined step, the bigger polynomial ax becomes ax equals a even with squares of x input plus x times a odd with x squared inputs. So I'm just going to give a motivating example here. So given a uh, as this polynomial, if we are going to split it, let's take the even index coefficients here indicated by blue-green. So that would be 1, 2, 4, and 6. And we give them new powers of x. Same goes for the odd index coefficients. In orange, x3 and 5, x3, 5. So to get back the original ax, we need to evaluate a even and a odd at x squared, as in we're going to put a value inside, but we're going to square it. And then finally, we multiply a odd x by x to recover the odd powered items. So remember, this is our combined step, and so this becomes ax. If you try to simplify this, it returns back to ax. For example, in this term, for x squared, you recover 4x raised to 4. For 3x squared, you recover 3x cubed, because this term will be multiplied by x distributed law. So we still have a problem. So which points to choose? So let's have another example here. Given polynomial a equals 1 plus x cubed plus x squared plus x cubed, we need 4 points here because we have a degree 3. So we need degree plus 1 points to represent this polynomial. So specifically, we need two positive negative pairs, if you remember from our divide step. So the positive negative pairs help in reducing the number of computations. If we start with 1 and negative 1 as our first pair, their square would be 1. But that's just uh, two points. So we need one more pair. So we need another positive negative pair whose square is the negative of 1. So what is the number whose square is the negative of 1? That would be the imaginary number. Thus, the second positive negative pair is I and negative I. But the problem is this works for 4 points. But can we generalize this for higher powers or more number of points? And the third core idea, something called roots of unity. So now this is the complex numbers part of FFT. So this is defined as the complex number omega, such that omega raised to n equals 1 for integer values of n. There are exactly n number of nth roots of unity. The power of an nth root is another nth root. And this is the formula that gives the nth roots for a given n. So for example, here there are 8 8 roots of unity. So you plug in 8 into n, and then you solve for it for values of k starting from 0 up to 7. Notice that if you reach 8, it wraps back around, goes back to k raised to 0. So roots of unity are periodic and they are equally spaced on the unit circle in the complex plane. So here are the neat properties of roots of unity that make it amenable for the divide and conquer strategy of FFT. Squaring n roots of unity produces half of it, n over 2 roots of unity. For example, squaring the 8th roots of unity produces the 4/4 roots of unity. Roots of unity are positive-negative paired, so this helps with the reduction of computation. For example, this is our motivating example earlier. The 4th roots of unity are plus minus 1 and plus minus I. So I hope it's clear how this helps with uh, the divide step of our algorithm, because if you're dividing uh, a certain number of size of a vector into 2, uh, it corresponds directly whenever you square the n roots, you get half of the roots for the next layer of recursion. We still need to do some processing for uh, our polynomial inputs in coefficient vector form. So the input coefficient vector needs some padding. So it needs some padding for the missing powers. It needs some padding for accommodating the required number of points to represent the result of multiplication, and for getting a power of 2 number of points. And I will explain why. So example, uh, p equals 1 plus 2x squared times q equals 2 plus x plus 3x squared. So I think you can already imagine that there's a term here where you get to multiply 3x squared times 2x squared. That would result to 6x raised to the 4. So whatever the new polynomial is, it's gonna have a degree of 4. That means you're gonna have to have at least 5 points for vector p. So the red coloring here means padding for missing powers. In this case, for vector p, it doesn't have a power for x raised to 1, so we add a 0 here. For q, it doesn't have missing powers, so we just write the coefficients as is. For orange coloring, we need the padding for the required number of points. So 3. So the degree would be 4. So we add another one. So 1, 2, 3, 4, 5. And as for the blue padding, it's the padding required for the divide and conquer algorithm. So as we know, the divide and conquer algorithm of FFT divides the input by 2 every time. So we're gonna need a power of 2 number of points. So in this case, the closest to 5 would be 8, because 8 equals 2 raised to the third power. So we add 3 more points here. So the final input vector for P would be 1, 0, 2, 0, 0, 0, 0, and for Q, 2, 1, 3, 0, 0, 0, 0, 0. So the idea is to apply FFT on vector P and then apply it on vector Q. Once we get another vector, we do pointwise multiplication with them, and finally do inverse FFT to turn them back into coefficient representation. So the FFT algorithm is shown here. This is taken from our reference, but I added some comments for as annotation. So this is recursive, so you have to have a base case, otherwise it runs into an infinite loop. Line 4 represents the computation of the nth roots of unity. Line 6 and 7 refer to the divide part of the algorithm, in which we gather the even index coefficients for line 6, and then for line 7 we gather the odd index coefficients, and then we apply the recursive FFT on those vectors. Lines 10 to 12 refer to the combined step. So The first one is on line 11. For combined step, we're filling up the first half of y, and then for 12, this is the combined step for the second half of vector y. So as you can see, the range of k here is from 0 to half of n, and then the rest fills up the vector y. And as you notice, this is similar to our first core idea earlier in the example. It's reusing the computations here. In this case, this is plus omega yk. Meanwhile, this is minus omega yk. And this is just some annotation from our book. Update omega variable to make computations cheaper, because in other implementations, uh, the function also takes the root of unity input. So in our book, it uses this explicit omega variable to make computations cheaper. So the running time is clearly n log n. The invocations cost linear time depending on the length of the vector, and there are a log n number of layers due to divide and conquer. So let's go back to our high-level overview. So the progress so far, we were able to reduce quadratic time down to n log n for FFT using FFT in the evaluation step. What about the interpolation back from point value representation to coefficient representation? So inverse FFT strategy is outlined by this slide. We represent evaluation as matrix vector multiplication. This is our forward FFT, in which we have this equation. So matrix omega times c vector equals v vector, where c is the input coefficient vector and omega is the matrix of roots of unity and v is the evaluation vector. So the idea is to represent interpolation as another matrix vector multiplication to retrieve the coefficients. But this time we're going to use the inverse of uh, the roots of unity matrix. We multiply it with v and then we get c prime. So in this case, w raised to 1 is the inverse of the matrix of roots of unity, and v is the same evaluation vector that we got from pointwise multiplication, and c is the output coefficient vector. It turns out that the inverse of omega is cheap to compute. It's just the same matrix of roots of unity, except every element in the matrix is just raised to -1 and then divided by n. So why does this work? So the omega matrix is actually called the discrete Fourier transform matrix, but we won't get into that now. Multiplying the DFT matrix with its inverse, omega -1, yields a matrix that is simply n in the main diagonal, as in from upper left to lower right, and then 0 elsewhere. Does that, if you took some linear algebra lessons, that's familiar. That's the identity matrix multiplied by n, where n is the size of the input vector. So to represent this in terms of the original omega, just divide omega with n and replace every member with the roots of unity raised to -1, or the reciprocal. So it's literally just one change of line of code in the FFT pseudocode to implement inverse FFT. And our progress is finally complete. So we start again with the coefficient representation of the two polynomials, do FFT separately on both of them, and we sort of merge them using pointwise multiplication, and after this we get an evaluation vector, and then we input this evaluation vector into the inverse FFT to get back the coefficient representations of the multiplication of a and b. So that completes our lecture. So the magic of FFT is that it happens in n log n, and it can be done to convert coefficient representations to point value representations and vice versa. There will be a full example in the paper. Thank you for listening. And here are my references. This is our book. This is online lecture notes where I got the most intuition from. And this is an accompanying video where I got some visualizations that improve my intuition of the algorithm. Thank you for listening.